Previously, we took a look at the electric field due to spherical charge distributions, and now we're going to transition to a special configuration that shows up a lot in electric circuits. It's known as a capacitor. Now, I'm drawing a bunch of extra space here, but we should understand that these plates are very large compared to the separation between the plates. I'm just drawing a small chunk of it. And in a capacitor, one of the plates will hold a charge plus Q, and the other one holds minus Q, uniformly distributed along the plates. So let's try to figure out what the electric field strength is in this zone, and this zone. So let's start by looking at some point over here to the left of our positive plate. So we can go ahead and think about the contributions from the electric field to the electric field from both the positive and the negative charge. So from the positive charge, the electric field at this location will be pointing to the left because it's pointing away from our positive source charges here. And from the negative charge, we know that electric fields will always point towards negative source charges. And since these are very large plates, we can treat them as infinite sheets of charge. And when we did that before, we saw that the electric field will always be perpendicular to the sheets in question. So we've got two contributions, one to the right, one to the left, at this point of interest. How do they compare? Clearly, we're closer to the positive plate. So would you say that the electric field strength due to the positive plate is greater than, less than, or equal to the contribution from the negative plate? Pause and we'll get back to it. Okay, surprisingly, because we are treating the sheets of charge as infinite, the contributions are actually equal. And so we get that the net electric field out here, we'll just write E, is actually equal to 0 out in this region over here. And if that makes you feel a little squeamish because you're looking at this saying, well, I can see that this is closer to this. Yes, but if this sheet is infinitely large, if you were to stand in front of an infinitely large wall, how would you be able to tell how far away you were from it? It would completely fill your field of view. Same deal here. So both contributions are equal and they cancel out. And we can go take a look over here in the right. If I look at a corresponding point over here by the same token, the contribution from the electric field from the positive plate and the negative plate will again be equal and opposite to each other. And they will cancel out to give us a contribution that's equal to 0 out in this region as well. So that just leaves some point in the middle. And it turns out it doesn't matter where we are because remember, the strength doesn't change with distance in the limit of these being infinite plates. So we just have to look at how the contributions are directed. The positive plate will be giving us an electric field contribution pointing to the right in this location, because the electric field will point away from a positive source charge. And since it points towards negative source charges, the contribution to the electric field from the negative charge will also be to the right. And since by the symmetry of the situation they're equal, we can note for the moment that the electric field strength is, say, 2 times the contribution from the positive plate. All right, so let's figure out what that is. For an infinite sheet of charge, we already saw that the electric field strength was eta over epsilon naught. So now we've got two of these. So the electric field strength for our capacitor will be 2 times that, or, I'm sorry, over 2 epsilon naught there. Will be 2 times that, so it's just plain eta over epsilon naught for our capacitor. Now, in practice, these sheets aren't infinite, but they're often very large compared to the separation. So you can put in a Q over A for eta if you prefer. Now, if you're still feeling a little queasy about this, we can go and spend just a moment comparing this ideal capacitor that we have to a real world one. So we can go ahead and draw field lines for our ideal capacitor that we just looked at, where the sheets of charge are effectively infinite. So if they're effectively infinite, so I'll just kind of draw dots going up and down so that we remember that the sheets go on forever. We can draw electric field lines, and we know that electric field lines always start at positive things and go to negative things, and there's no way they can ever cross. So the only way this is going to happen is if all the electric field lines are parallel. So something like that. So now if I want to find the electric field vector anywhere, like let's say right here, well, the field vector at that location needs to be tangent to the lines, and its length will be proportional to the density of the lines. Well, the density of the lines everywhere is equal, because if it weren't, then you would be able to tell where you were up against our infinite sheet of charge, but then it wouldn't be infinite anymore. So no matter where you are, the electric field strength is the same, and it points in the same direction. So that's for the ideal case. And believe it or not, for practical electronic devices, this is not unreasonable. They've done amazing jobs in being able to take plates that are on the order of square meters and putting them into compact packages where the plates are separated by less than a millimeter. That's pretty close to infinite. That's not too bad at all. But let's go take a look at, say, a real world case here for our parallel plate capacitor. So in the real world, where the sheets aren't infinite, so I will now not draw little dots to remind us of our for the sheets being infinite, because they're not. So these are a finite extent. So now if I start drawing electric field lines, yeah, if I'm in the middle, say here, the electric field lines will be doing something like this. But out at the edges, there will be some pin cushioning starting to happen, like this. And you can see the spacing of the lines gets larger, so the electric field is weaker out here. And in fact, there will even be, whoops, got my arrowhead pointing the wrong way there. In fact, there will even be a small number of lines coming in from and going out to infinity. So what we have outside the capacitor is what gets called the fringe field. and it's much weaker. Oops. Than what's inside. Alrighty. So we can go ahead and start to think about what would happen if, say, a charged particle were moving through such a configuration. So the first case I just want you to think about for a moment is, let's say I've got plate here, oops, plate here, plate here. Let's switch it around. Let's say got negative charges here, just for the fun of it, and positive charges here. So in this case, the electric field lines are pointing to the left. Now with that, let's go take an electron and place it right there. So I just placed it there. It's initially not moving. I'm going to let it go. I want you to predict what will happen to it. So pause and we'll get back to it. Okay, so it turns out that it is going to accelerate to the right. And so how does that make any sense? Well, if we take a look at this, remember that the force that any charge feels will be the charge itself times the electric field at that charge location. So here, the charge is negative E. So that means that the force will point in the opposite direction of the electric field. So here, this would be negative E times our electric field pointing to the left, and the negative of left is right. And then by F equals ma, the acceleration and the force, net force, always point the same way. So we wind up accelerating to the right. All right, well, let's try another one here. And this will be a little more complicated. This time I will make the negative plate at the bottom, and we'll have a positive plate at the top, like so. There we go. So first off, just ask yourself, which way are the electric field lines going to point between the plates? That's correct. They point downward. And since I made this a very large capacitor, we're going to approximate it as ideal. So we'll pretend that outside the capacitor, the electric field is 0. So again, let's bring back our friend the electron. And we will have it moving initially horizontally to the right. I would like for you to predict what is the shape of the path that the electron will take as it goes between the plates. Okay, so as we approach the plate, here let's change colors to make the path more clear. So as we approach the plate, straight line, when we get into the zone here, where we have an electric field, the force will be up, and it will be a constant force up. And we've seen what happens when you have constant forces down, right? That's gravity near the surface of the Earth, and we knew that things moved in parabolas then. That's still true now. This will move in some section of a parabola and then head off in a straight line. So right in here, this is a chunk of a parabola. And then inside and outside, they're straight. All right. Now let's go ahead and revisit this first example here, just this time with some numbers, just to maybe get a little more concrete of a feel for it. So let's say that we've got ourselves a 500 Newton per Coulomb electric field pointing to the right. Doesn't matter what's causing it. We can imagine that we're inside a giant capacitor or something like that. So we'll go ahead and place an electron, like so, initially at rest. So we'll say that it travels 10 meters. What I want to know is both the magnitude and the direction of the final velocity of the electron. All right, so remember, the way you solve any physics problem goes by the acronym STAR, which stands for Situation, Tools, Answer, Review. I've drawn the picture, I've identified the unknowns, and the knowns, so I understand the situation. So now the next thing is to figure out the tools. Seeing this, asking for V final, being told 10 meters, seeing a V initial of 0 here, this is starting to look an awful lot like kinematics, and that makes some sense. Now, in order to do kinematics here, we don't have enough information. We need to know either the time or the acceleration in order to have enough information to solve this problem. We can work out that since the electric field points to the right, and this is a negative charge, that means that my electron will feel an electric force to the left. So one of my tools here is going to be Newton's second law. We can say A equals F net over M, in which case this will be equal to minus EE over M. So we've worked out that the acceleration is EE over M, and we know that the direction is going to be to the left. So we know now that we will be traveling our 10 meters to the left. All right. So now that we've gotten ourselves an acceleration, we can now go ahead and do kinematics. And since time was neither asked for nor given, you can use the kinematics equation that doesn't have time in it, which is V final squared equals V initial squared plus 2A delta X. V initial is 0. Now, as a general rule of thumb, you should never, ever substitute numbers unless we're doing Kirchhoff's laws stuff, in which case knock yourself out because it won't matter anyway. The one exception to the don't put in numbers rule otherwise is it's generally okay to put in zeros because they tend to make your life easier. So we already know that when we get over here, in order to have gone to the left, it must be that V final is pointing to the left. So we've got our direction, left. We just need to get this. We have the magnitude of the acceleration, so it'll be 2EE over M delta X. So V final equals the square root of 2e over m delta x. And notice that I'm still leaving this all as letters. In part, this is because it's easier to catch your algebra mistakes, and also it avoids things like accumulated round-off errors, which can really throw off your answer to a problem. So now, when you substitute in the values, you don't just put in the numbers. All these numbers have units, so you should always put the units in with the numbers to make sure that everything checks out. So, okay, we got a 2. So this is the fundamental quantum of charge, 1.6 times 10 to the negative 19 coulombs. Remember, all physics constants are positive numbers. The electric field strength is 500 newtons per coulomb. And the mass of an electron can be remembered by saying call 911. So 9.11 times 10 to the negative 31 kilograms. And then we said the thing traveled 10 meters. So when you crunch it through, you get that it is 41.9 times 10 to the 6 meters per second, and we already worked out the direction that it was to the left. So basically 42 million. So that should already be making you feel pretty good about it, because yes, I'm that big of a nerd that I would probably, when I write a problem, try to get it so that I get at least close to something that looks like the answer to the ultimate question of life, the universe, and everything. And if you don't know what that is, Google it. It's worth it. But otherwise, you should at least ask yourself, it's kind of hard to tell with these problems what's reasonable and not or not. I mean, this is tens of millions of meters per second. But at the very least, for a sanity check, you can ask yourself, is it going a lot slower than the speed of light? Because if it weren't, then we would have to be using relativistic expressions. Well, the speed of light is 3 times 10 to the 8 meters per second. This is 4 times 10 to the 7. So, a little more than 10% of the speed of light. That's still going slow enough that classical physics actually works out okay. All right. So in the next video, we will go ahead and take a look at what happens if you stick a dipole into an electric field. Catch you over there.